What kinds of blocks do you need to model 1.253 or 1 and 253 thousandths? What did you use? How many of each? Okay, 2 flats. Oh yeah, 2 flats. 5 little rods. And 3 little cubes. Okay, so we have 1, we have 2/10, 5/100, and 3/1000. The name of this number is 1 and 253 thousandths. Okay, we always name it by the last decimal. Okay, and we always use the word "and" to represent the decimal. So those are important things that kids need to know. They'll say words like 257 when it really should be 257. So you don't use the word "and" in a whole number, you use the word "and" to represent the decimal. Okay? That's an important thing that we need our upper elementary and middle school kids to learn. It is not proper mathematical words to use to say "and" in a whole number. So I would never say 1,256. I would say 1,256. Okay? And is only used to represent the decimal. Okay? So it's 1 and 253 thousandths. Well, you can say decimal informally, but the proper name of this number is 1 and 253 thousandths. Okay, and that is to distinguish. Here's an important thing, folks. Here is an important reason for this. Okay? How would you read this top number? Yes, Becky. Okay. 205,000. Some people might say it 205,000. But that would be confusing because how would you read this number? It's a very subtle difference. But then when you put the such a subtle difference, and many people will have a very hard time making that difference. Okay? It's an important thing because this word 205 thousandths sounds very similar to 205,000, right? So that is why we don't use the "and" in whole numbers. And now you know. So this is 205 thousandths. This is 205,000. Okay. It's also important that kids know that you can model these in different ways. Yes?
I think it's also helpful that if you give someone this one, you should probably give them some.
Okay. We should probably have more than that.
Or you might have students sitting there freaking out because it doesn't work.
Or just her.
Okay. 25 rods and 3 little cubes, and that value is still the same. So even when you're introducing decimals, try to get them to think about, could I have represented this differently? We don't have probably enough cubes at your table, little cubes, but we could have made one big cube and 253 little cubes, right? To show that I have 253 thousandths. Okay, so there's all kinds of different ways that you can show it, and it's important for kids to know that you have that flexibility, because that's what allows you to trade, right? That you can represent it in different ways. You'll notice I put a couple up here that have internal zeros, right? 1 and 5/100ths, or 1.05. Kids sometimes get confused about what to do with the zeros, so it's important that you ask them to model ones that have internal zeros, right? So how would you model this one? What's 1? A big cube. Whoops. So 1 big cube and 5 rods. Okay? So kids sometimes get confused about internal zeros and how come there's nothing there. And sometimes you'll get them to do them on a place value map so that they realize that when they have an internal zero, it means there's nothing in that space. Okay? And that's important when you're doing whole numbers too, right? If you're modeling 206, you want them to model 200s, 0, 10s, and 6. Right? Same thing. So what would you use for 0.301? How would I say that? I would say that as 301 or 301 thousandths. No, 301 thousandths. Yeah, we're gonna get it. Oh, right. Sorry. Yeah. So this would be 3 flats and 1 little cube, and this one would be 2 big cubes, no flats, 3 rods, and 1 little cube. Okay, good. All right. So how did we model addition? What did you do with 0.35 plus 0.47, or 3,500 plus 4,700? 3 flats. And 5 rods. Good. And then 47. So there's 0.47, so 4 flats. 7 rods. Whoops. Oh my. Messing everything up. And then you clustered things together. And what did you end up with? The number. 8200ths. So you ended up with 500ths and 700ths, which gave you 1200ths, which gave you another tenth, right? And 200ths, so you could regroup. Okay? So we end up with 0.82. Okay, you want to do some subtracting? How do you model subtracting? I'm going to move this onto another page so we have enough space. 0.235 minus 0.381. How did you do that? Okay, so let's start with 1.2. Oops, forgot to change that back into an infinite corner. Okay, so we've got 1.235. What do we need to take away? Okay, can I take away 1,000? Are you sure? Because I see one right here. So I'm going to take away 1,000. I'm going to put it down there. Good with that. Okay. Can I take away 8 hundredths? I have 3. I can take away 3. What else will I have to do? Take 5 from this. So I could trade this for 10 of these, right? Okay, so I've traded that for 10 of these. Now I can take away 5 more. So I've got my 8 and my 1, and now I need to take away 3 tenths. Can I take away 3 tenths?
Yeah, take 2 out of the big one.
I need to take 2 out of this. So again, I can trade this for 10 flats. Okay, so I'm going to put these 3 over here. How many am I left with? 8. So I'm left with 0.854. Good. Okay. Okay, let's take a look at this one. 2.15 minus 0.936. Let's throw up a new page and throw that on there. How might you go about doing that one? Is there a way we can think this through without kind of modeling? Is there a way you can reason it out? How would you do it?
Work it by place values.
Okay, think about it by place values. Okay. I want to take away 9 tenths from 2.15. Can I do this mentally? Oops. You know what that would be? How'd you get that?
How did I get that?
Mm-hmm.
Take 9 tenths from 21 tenths,
Okay.
and you get 11 tenths and 5 hundredths.
Okay. So 21/10, I can take 9/10 away from that, right? And I'm left with 12/10, which is 1 and 2/10, and I still have my 5/100ths there. Okay? Another way to think about that is to take away 1 and add 1/10 back on. Can I now do 1.25 minus 0.03? Can I take that away? How would I do that?
1 and 2200.
Okay, that one's a straight addition, right? Or straight subtraction. Because I don't need to regroup or anything. There's 5/100ths there. I need to take away 3/100ths. That's easy to do. So now I have 1.22 minus 0.006. And so I have no thousandths over here right at the moment. But I can assume that that's a 0, right? I have 0 thousandths. I need to take away 6 thousandths. What am I going to be left with?
1.214.
1.214. Okay? 1 and 214,000. Okay? So you can use some of your mental math strategies. Once you have internalized the whole notion of base 10, like once you have base 10 down, you can extend that to understanding that as long as I know a place value, I can take some of a place value, right? I can break it apart and look at it in terms of the place values. And I can always know that I'm taking something away from something. Okay, we've got more on the next page. Let's try some of these mentally. See if we can think of using our mental math strategies to do some of these. Okay? We're going to try and use some of our strategies that we learned before to do some of these. If I had to add 2.98 plus 4.35, what might I do? Any thoughts?
Add the whole numbers first.
Okay, that's one strategy. Add the whole numbers first.
Make 2.983.
Oh, how could I make 2.98 into a 3, Dennis?
Adding 200.
Take 2/100ths from the... Okay, so I could make this 3 plus what?
4 and 3,300.
I could make this 3 plus 4 and 3,300ths, couldn't I? And now it's the answer. Isn't that a sweet thing? Okay? So those mental math strategies that we learned for whole numbers, if we understand place value, work for decimals too, right? Okay, what about this one? Craig, let's try your strategy for this one. Add the place values. Okay, so 3 and 2 is? 5. I'm going to do it this way. 3 and 2 is 5. 1/10 and no tenths is? 0.1 plus nothing is still 0.1. Okay? 2/100ths and 6/100ths? Sorry. sometimes if you do a front end, you can do quick adjustment. So I might have said 5.1672, right? Let's do this second subtraction one first, because it's easier than the top one. Why do I say this one's easier? When you look at it, what do you notice? It's simple subtraction. That is exactly what it is, because there's no need to regroup anything, right? Every digit in the second number is less than its corresponding place value in the first number. And kids need to know that when they quickly look at something, they need to have a quick look at it and decide, can I just do this with simple addition or simple subtraction? Okay? So I can just think 4 minus 3 is 1. 3 minus 2 is 1. And 5 minus 4. So I end up with 1.11. Okay? So when you have that unique situation where all the numbers that you're taking away are less than their corresponding numbers in terms of place value, you can just do that straightforward front end subtraction. Okay? Because there's no regrouping. Okay, so now let's talk about this one. Any suggestions what you would do here? What's your idea? Add 15 to the other side? Okay, now make sure with subtraction that we're not changing it up. Okay? You're on the right track. But with addition, I can take from one and give to the other because I can just slide stuff over because I'm combining. With subtraction, I can't take from one and give to the other. I have to take from both, right? So if I think about 2.146 being here on the number line, and 3.015 being here on the number line, if I want to make this go back to 3, then I need to make this go back the same amount. So could I take 15 thousandths from that? What would I be left with? What value would I get here? 2.131. So now I'm going from 2.131 to 3, and what's a good way to do that? So I've changed this instead to 3 minus 2.131. How do I kind of get my difference? I had to move this back 15 thousandths to get to 3. So I had to move this back 15 thousandths. So if I subtract 15 thousandths, 4 minus 1 is 3, and 6 minus 5 is 1.
If you wanted to, you move both sides 4. But if you still have the same, you have a certain amount of objects, as long as they're the same, you take them from one.
No, that's with addition. Okay? If I take them from one, I give to the other, but we're subtracting. So I'm trying to find the difference between these two numbers, which is the distance between these two numbers. So if I slide one back, I need to slide the other one back. Megan, you had a question.
I never mind, I thought of it. Okay.
So what's a good way to get from 2.13 to 3? I need 9 more, but I don't really need 9 more because that would be too much because I already have here 100s. So I know I need 8 more.
Why would you start with the
You could, but because I like to make 10s and make 100s. So I know I need something to make 100 here. What goes with 31 to make 100? Okay, 69 goes with 31 to make 100, right? So I end up with 0.869. So I can make, really what I'm making is a tenth, but I'm thinking 31 plus what makes 100? Right? 31 and 69 make 100. Okay? Does 30 and 70 make 100? So if I had 69 thousandths, that would make a tenth, and then I'd need 8 more tenths to get to 3. So you're using a think addition and a make one strategy here. You did that one that way? Yes.
I did it at 3 minus 2, 1. So 1 minus 1.
Okay, that's another way we can do this one.
I broke it down until I got the same spot correct, and then I just did it.
What was that other number? 2.141?
146. So I took it down to 3 minus 2.131. And then took the whole of 3 minus 2 and then looked at what I had left. And I just did 1 minus that.
Okay. So you could do this as 3 minus 2, right? Which would give you 1.015, and then subtract 0.146 from that as well. And then you could start breaking it apart and looking at what's left. What's the difference? Is that what you did? No, that's not what you did.
I did it the same as the one before. Like I took the 0.015 off to each side, and then so that I was left with 3 minus 2.131.
Oh, okay.
And then I looked at the whole, so I have 3 and 2. So I did 3 minus 2.
Okay.
1 minus
0.131. Yeah. So you ended up with 1 minus 0.131. And rather than doing a think addition strategy, you just took it away in parts, which works as well. Okay. So the point of this conversation, though, is that if we have good understanding of place value, the operations come out. If we don't, it's going to be problematic. I probably have told you this story before, but I had kids who wrote this recently. What did they do? They added 31, 9, and 8, didn't they?
Oh.
So they didn't have a good understanding of place value. And sadly, every kid in the class did it the same way. They understood the problem, they knew they had to add 3 numbers, but they had no understanding of place value with decimals. And so they were applying their whole number sense, lining up the digits as opposed to lining up the decimal place, right? So it's really important that we spend a lot of time with kids modeling decimals and getting them to think about what the place values mean, because once you understand place value, the operations become much easier. Let's try and do some multiplication, shall we? What does multiplication mean? Repeated addition, multiples of, or sets of, or jumps of, or rows of, area, it can be an area, right? So for this, because I have a whole number times a decimal, I'm going to think sets of. So I want to build 2 sets of 1 7/100. Okay? So what would that look like in terms of our models? 7/100. Oh, sorry, those are supposed to be rods. Sorry.
Well, something that simple though, you have to.
No, you would only do the drawing of it maybe once or twice to make sure everyone's on the same page.
Well, then,
Yeah. You want them to see that it works, and once they know that it works, then they can just kind of figure it out, right? So, I built this twice, right? So I can cheat. Just clone it. Oh. Okay, so I've got two sets of it's all messed up, but I've got two sets of 1 and 7/10 or 7/100, which gives me 2 and 14/100. Right? Okay, and you can have kids write these out in parts, so they might do like 3 times 2 is 6 for this one. 3 times 1/10 is 3/10. 3 times 4/100 is what?
What grade is this at?
This would be grade 5 and 6. We start doing groups of decimals. Whole numbers by decimals. We explore a decimal by a decimal in grade 6, so we're going to look at that in a minute. Okay, so 3 by 2 is 6, 3 by 2/10, or 3 by 1/10, sorry, is what? 3/10. 3 times 0.04 is what? 0.12, right? Good. And 3 times 5,000. Okay, 0.015. Okay, and then you can add your parts up, so then you have to pay attention to place value, which my thing is so messy, it's really hard to see where place value is, but you get 6.4. Where am I? 3.5. Thank you. Okay, so you can always do these in parts, and you can add them up using the distributive property, right? So if we can use the distributive property to multiply a single digit by a multi-digit whole number, those same properties apply when we're multiplying a whole number by a decimal, okay? But when we get into multiplying decimals by decimals, that becomes a little bit more interesting. Okay? The best way to think about multiplying decimals is the same way we thought about multiplying fractions. The area model. So we had an area. Oops. That's not an area. Grab the square, we will. Build a rectangle. So if you take your flats out and you stack a length that is 1 and 3/10, what you're going to fit in here is a flat and 3 rods. Okay? The flat has a height of 1 and a width of 1. That's why it has an area of 1. A rod has a width of 1/10 and a length of 1, so its area is 1/10. So then I need to stack 7/10 going the other way. of this is 1 3/10. The width of this is 1 7/10. You good with that so far?
Yeah.
What is the area? What's the area of the flat? Right here. What's this? 1. 1 whole, right? And where does that come from? How do you know that's 1? Because it's 1 times 1? Oh, okay, good. Yeah, it really is that simple a question. 1 times 1 is 1. What's the area of this piece up here? 0.3. It's 3/10. How do you know it's 3/10? Because it's 3/10 times 1, right? 3/10 times 1 is 3/10. So this is 0.3. What's the area right here? 7/10. Because it's 7/10 times 1. One set of 7/10 is 7/10. And what's the area of that little bit up here? 21 hundredths. 21 hundredths, right? 3/10 times 7/10 is 21 hundredths. Okay? When we take a tenth of a tenth, we make a hundredth. Okay? This model is really important. I didn't have to tell you to move decimal points or count up places and blah, 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 crazy stuff. Right? I can see that a tenth of a tenth is 100. So now I can add these things, and luckily for me, 7/10 and 3/10 go together to make 1. So I have 2 and 21 hundredths. Okay? So we learned how to do this when we learned how to multiply 2-digit numbers, right? When we learned how to multiply two-digit numbers, we did things like 13 times 14 and 16 times 18, and we broke it into 4 partial products. Right? This is all based on what property?
Unit. No. Distributed.
Distributive property. What we're really doing is doing 1 plus 3/10 times 1 plus 7/10. And we're multiplying 1 by 1, 1 by 7/10, 3/10 times 1, and 3/10 times 7/10. Okay, so this is distributive property. It does. I call him Binomial George sometimes. Okay. So just the same way we did this with whole numbers, we can do it with decimals. The nice thing about multiplying decimals with the area model is when you multiply a decimal by a decimal, you see why we end up with extra decimal places, right? Because when I multiply a tenth by a tenth, I get hundredths. So then it shouldn't be too far for me to figure out that if I took a tenth of 1,000, I'd get a 10,000, right? So again, that kind of connecting that whole notion of taking a part of a part to multiplication when we're dealing with numbers less than 1, right? Between 0 and 1, we're really taking a piece of a piece. So how might you calculate this? You could? Yeah. What else might you do?
I might do it all in my head.
You might do it all in your head. And when you you do it in your head, are you like lining them up and carrying stuff and moving decimal places? Like
Well,
you were drilled to do?
Maybe I can explain this.
Okay.
I would go 1 times 2.35 is 2.35, and then 0.2 of 1 is obviously 0.2. So the 2 from 2.35 is going to give me 0.4. And then 0.2 of 0.35 I know is 0.07. So 2.35 plus 0.4 plus 0.07 gives us 2.82.
Okay, so you're breaking it in parts, really. You're doing one set of 2.35, and then you're doing 2/10 of that.
Yeah, it'd be tough to do it with other numbers. That's just one that works out.
Yeah, no, that's right. But you can break it into parts so that you can do one set of 2.35, which you already know is 2.35, and then you can do the 2/10 of 2.35, which if you wanted to do that, then you can do that in parts. So you can do 2/10 of 2, right? Which gives you 0.4. You can do, and you did 2/10 of 0.35. Is that what you did?
Yeah.
And
It's
you
just
knew
like
that
dividing-
was.
It's just like dividing the 35 by 5, because you know 0.2 is 1/5
Oh,
of
isn't that
1.
interesting? You can divide the 35 by 5 because 0.2 is 2/10, which reduces to 1/5, right? So you could think of this as 1/5 of that, and which we learned the other day is 1/5 times by 1/5 is dividing by 5. So he has that mental math strategy down where he knows that that is 0.07. Okay, good. And then you can add that up, and you're good to go. Okay, so we're just going to make the page bigger. So we've got a set of 2.35 plus 0.47. Okay? We will let kids explore these using some mental math properties, but we don't expect them to be able to do them mentally. Okay? But we should be able to let them explore some of these, and this is grade 6, 7. Okay? They can explore them, but it's a tedious calculation. So when we have tedious calculations, what do? Use technology. Oh, did you? That's right. The appropriate use of a calculator is not to multiply 3 times 4. That one you need to know in your head. The appropriate use of a calculator is when it becomes messy and when it becomes tedious to do. Okay?
So, can you do area model? You can't do area model with anything.
You can kind of do area model. But it really becomes kind of a regional model, and you just have to remember about your place value rules. So I could do, can you tell me what the question was again? Because I can't remember. It was 2.35 this way, right?
And 1.2.
Okay, and so when you do it this way, you can actually do 6 partial products, right? So you can do 1 times 2 is 2. 1 times 3/10 is 3/10. And 1 times 5/100 is 5/100. Right? Which we already knew from the 1 times the whole thing. And then you can do 2 times 2/10 is 4/10. Right? 2/10 of 3/10 is 6/100, right? And 2/10 of 5/100 is 10,000, which is 1/100th again. Okay. Some kids might like to write it like that, just so they see the 10 there. 2 times 5 is 10. And then we can add those all up. Now the nice thing about that is you add your place values along the diagonal. And this one actually gets regrouped, right? But it really would have been thousands if it was something else. Okay? You like that?
Yeah, I like calculator better. For that one. I like calculator better for that one.
Yeah. But it's important that you understand that all these different models will still work, even though we have these different decimals. The other thing that we do with kids is we spend a lot of time doing multiplying by patterns and dividing by patterns of decimals. So if I know I can multiply by 1/10, and then I multiply by 100th, and I multiply by 1,000th, what I notice is the pattern of how the decimal place changes. Okay? So if I take 3 times 1, I know that's 1 because I can build 3 cubes and show that it's 1. And if I take 3 times 1/10, I know that's 3/10 because I can build it, right? Oops. Honestly, you should really correct me when I say stupid things. If I take 3 sets of 100, I can build that with 3 rods, and I see that it's 300. And if I take 3 sets of 1,000, I can build 3 little cubes and see that that's 3,000. So from that, I notice a pattern, right? So if I had to do 3 times 10,000, even though I can't see it because I don't have a slice of my little cube, what do I know it's going to be? 3 10,000s, right? And I start to see this pattern of digits. And this is where that whole crazy move the decimal point thing comes from. It comes from this pattern of multiplying by digits. Now you've been dying to learn how to divide, right? Still trying to figure out the multiplication one? Now you just add up all the numbers. So you can put these two together. What does division mean? Equal sharing, that's one way. What else does division mean? Just equal sharing? It could be breaking it into a certain number of groups, or it could be making groups of a certain size. If I say 3 3.12 divided by 6, do you think I mean make sets of 6 out of 3 and 1 and 1200s? Would it be easier to think of taking 3 and 1200s and breaking it into 6 equal groups? Yeah, easier than making sets of 6, isn't it? Okay, so I could break that into 6 equal groups. Now here's a strategy we might try. Okay, I want you to watch this because you're going to use this with both whole numbers and decimals. Okay, this is an alternative to long division. It's using estimation and multiplication to figure out your solution. So much for the kids.
Oh, and the ranch.
I want you to think of something that when I multiply it by 6, I get really close to 3. Sorry, I heard something. Decimal 5. Would you agree that if I multiplied 6 times decimal 5, I'd get 3? Okay, so I can get to 3 by using decimal 5. I'm going to take that away. I've covered that already. Now I need something that's going to get me close to 1200ths. What would I multiply by 6 to get close to 1200ths? 200ths. In fact, that might get me exactly 12. Right? 6 sets of 200ths is 1200ths. Okay? And I have nothing left to share. I've fair shared it out. So what would be in my 6 equal groups? I put 5/10ths in each group, and I put 200ths in each group. So all together I would have 52 hundredths. Okay? We would start by fair sharing these and then move to this strategy. But even with whole numbers, if I was doing 312 divided by 6, I would get kids to fair share that first. But then I would expect that they would think 6 times 50 is 300 and 6 times 2 is 12, so I can put those together. So we want them to take those strategies that they've used with whole numbers and now apply them to decimals. Okay?
So you're not moving the decimal.
No, we're not doing any of that crazy stuff.
So you shouldn't get them at all to do it like the other way, like where it just goes.
I don't even know what you mean when you say it the other way.
I know. Well, the way I did it was, I'm not gonna say it goes into, but it just if instead of doing that, I just put a 0 there, and then said, okay, well, 31 divided by 6 would be 5 with a remainder of 1, and then carry my 2 down.
It's not a remainder of 1, though. It's a 10.
Well, yeah, okay.
So I will give you, what can I multiply by 6 to make 3?
Okay. So you want
And you can write it up there. That's right. 5/10 times 6, or a half of 6 is 3. So 5/10 times 6 is 3. I can take that away. I have 12 hundredths left to share. 200ths times 6 is 1200ths. If you want to write it that way, you can, but make sure you language it properly.
Yeah, that's the thing. It's hard to do it that way too, without saying goes into. Is that the only
Yeah,
time you do it?
but kids won't learn gazintu unless we teach it to them. We can cure children of the gazintus by just not passing it on. It's a communicable disease, the gazintus. It gets passed from teacher to student, generation after generation. Okay? We really need to use the language of fair sharing for division because that's what's going to help kids to actually they can just think about, like, how could I make 3.1 in 6 groups? Like, they might use a think multiplication strategy for this one, because they're kind of both nicely divisible by 6, right? 3 over 6 is half, and 12 over 6 is 2. Yeah. You sure can. It does. And so what we want kids is to go from the drawing. We would want to do modeling, drawing, and then have them internalize it. But know that if they're confused with one, they can go back to the drawing, right? And they can always check with a drawing, or they can always check with a model to make sure it works. Or they can check with multiplication. If I have 6 sets of 5/10, I can visualize that, and does that make 3? Right? And if I have 6 sets of 200ths, does that make 12 hundredths? Right? So you can have them visualize and check with multiplication as well. Okay? Keep in mind that by the time we're doing this, we're in grade 6 and 7. Okay? So we want whole number sense down, and we want them to be applying that to decimals so that they're internalizing it and visualizing it. Right? Now, if you're really good with mental math with the second one, you could take 2 and divide it by 4 and know that it's a half, and then play around with some compensation to kind of get it down to what you want. That's not always easy to do, so we're going to do this one out in a similar fashion. I'm just going to clone this page here so we can have a whole page to ourselves.
Lisa?
Yeah.
The parts due that for our unit plan, are we pass those in for feedback, or are you grading those?
I'm grading them.
Oh, okay.
Yeah. You can have the option of revising it if you so choose, but
Yeah, I know, we just weren't sure if they were.
yeah. Just, it's a way for me to give you feedback and get the grading done in pieces.
Okay, yeah.
So that I'm not all doing it in March.
Okay.
Okay, so what if you were going to do this one? How about you do it? What's your first thought?
Here's my first thought.
What's your first thought, Dennis?
I want to change that into a 2.
Okay, you want to change it into a 2?
Yeah, is it too complex to say, okay, if I have to add decimal 0.25 to make it 2, then I can subtract it from the other side of the equation?
Yeah, it's going to be a mess,
That's crazy.
right? But what you can do with your brain, making it 2, is you know, well, if I divided 2 by 4, what would the answer be? 0.5. So my actual answer is slightly less than 0.5. Now, what I need to add here is 0.25. If I broke that into 4 equal groups, or 0.025, if I broke that into 4 equal groups, right? It's going to be 0, 0, 6, 5. So it's going to be about 600ths or 6,000ths less, right? So you can get a good estimate by thinking about it as 2. But you're not going to get the exact, okay? And we would do very few of these using long division or any other sort of division strategy. Another way you can do this, which is a strategy you might not have thought of, but you can half and half. Well, if multiplying by 4 is double, dividing by 4 is half and half. So you can cut it in half and then cut it in half again, right? But because I put a 5 at the end, that makes halving kind of challenging. So let's use the strategy we just did. Okay? And I'm going to try and get close to something by multiplying 4 by something. What would you like to multiply 4 by? 0.4.
0, 0.
3 thousandths gives me 12 thousandths, right? Left with 3 thousandths. $3 divided into quarters. Take $3 and divide it into 4 equal parts. If I share $3 amongst 4 friends, how much did I give them each? 75 cents. Okay, but we need to adjust. So we could say that is 4 times. We need to make sure that our decimal places are right. So it's 4 times 0, 0, 0, 7, 5.
By the time you get to this though, would they not be well versed in language?
They would use a calculator, absolutely. I just want you to see how the process works. Yeah? And I can't fit my 5 in there. Okay, which gives me my. And we're done. You need to do 1 or 2 of these to make sure kids understand the process, because we're going to do some dividing in a bit. That's going to take fractions. Well, not in a bit because we're going to run out of time. But we're going to do, well, we might have time to do 1 later. We're going to do some dividing of fractions into decimals, so we need to kind of know how to do this process. So then I can then add up all my bits. So I have 4375 at the end here. And as I go back up, I have had 2 tenths and 2 tenths, which gives me 4 tenths, right? I had 5 hundredths and 4 hundredths, which gives me 9 hundredths, and then I had 3, 7, 5. Okay? So the process works by breaking it up into pieces and estimating. You don't necessarily have to always use a traditional algorithm. In fact, this one is much better at reinforcing estimation and place value sense. Yeah. Yes, you didn't have half. You did quarters. Oh, okay, yeah. You broke it into 1.6. Yeah. Oh, that's nice. That's really nice, actually. It's very, very good stretch. Yeah. And I couldn't fit it on the page because I ran out, but there's a 5 here. Because remember we were talking about quarters? Okay? Again, by the time you get to this point, this is a tedious calculation. As long as kids understand that they can fair share. The main thing is sometimes kids will fair share and they'll get a decimal remainder, and then they don't think they can break that remainder down. Right? They think these are limiting because the blocks limit them. So we need to tell them that, you know what? You could imagine this little cube is really like this big cube, and it can be broken down and broken down and broken down again. Right? And you can keep breaking it down. You can keep going. You can always break that into tenths and break that into tenths and keep going and breaking things into tenths. Okay? And speaking of breaking things into tenths, let's take a look at the other sheet. We're going to skip over to the other set of sheets, the one that has the table in it. Okay, so have a look at this one that says fractions, decimals, and percents. We're going to get started talking. We'll talk more about percents next day. But this is the one that's stapled. So a half is 5/10 or 50 hundredths. If I say this is 1 and I'm using decimals, 50 hundredths are shaded or 5/10 are shaded. Okay, so as a decimal, I can write that as 0.5. 5 of the 10 columns are shaded. Or I can write it as 0.50, right? Because 50 of the 100 squares are shaded. And it's important that kids learn that these numbers mean the same thing. And in fact, I can keep writing more and more zeros after that, and it's always equivalent to 5/10. 5/10, 50 hundredths, 500 thousandths, right? 5,000 10,000ths, and so on. You just want kids to know that those things are connected, that they're equal, and that it doesn't matter how many zeros you add on, it's still equivalent. Yeah. So that's pretty much how far I go with that conversation, right? But it's amazing how many kids cannot write an equivalent decimal that is equal to 0.50. Right? They don't know that that can be written as 0.5, which is an important understanding. Particularly like from tenths to hundredths. Think about that problem I just showed you with the kids who added 9/10, 8/10, and 31 hundredths and got 48 hundredths. Right? They didn't realize that 9/10 was 90 hundredths. So it's really important that they know they can add a 0 and then line up their digits if they're going to do adding decimal places, okay? And then we can talk about that as also being 50%, because percent means per 100. So it's 50 out of 100, okay? So what we want to do is we want to think about, what would other fractions be as decimals? How might I show 1/4 of this square? I might show half of a half. So split it in half. Whoops, split it in half, split it in half again. My lines are pretty bad. Let's try to be a little more neat. Okay? And would you agree that that's a quarter? And so what is that as a decimal? 0.25, because it's 25 hundredths. Okay? So we can take fractions and turn them into decimals by thinking about a hundredths grid and shading a fraction of a hundredths grid, right? We could have also taken a flat like this and said, well, I want to fair share it in 4 equal groups, so then I'd have to start trading, right? So if I took a flat and wanted to fair share it in 4 equal groups, how much would go in each group? 0.25. I'd take and I'd share 2 rods in each group, right? And I'd use 8 of them. So I'd have 8 of these done, shared, and then I'd have 20 little squares left to share, and I know I can put 5 in each one, and I can also show it this way. So one is by shading, and the other is by sharing. Shading and sharing. It's very exciting. So how might I show 2/5? Do you think 2/5 would be easier by shading or sharing? Okay, so let's shade 2/5 of this. What does a fifth of this square look like? 2 rows. 2 rows is a fifth, right? So if I break this into fifths, it looks like this, or 2 columns, whatever. And 2/5 is 4/10. Right on. I take 100 square and I break it into 5 equal parts, each part has 20 squares in it. So I'd have 40 squares or 4 columns, 4 tenths, or 40 hundredths. Okay? Sometimes we'll just get kids to convert to an equal fraction, equivalent fraction that's over a power of 10. Right? So some kids might have been able to look at that and said 2/5 is 4 tenths, so 4 tenths I can write as a decimal. Okay? If I use a fair sharing strategy, what I have to do is break it into 5 equal groups and then take 2 of those groups. So I'd have 5 equal groups, each group would get 2 rods. But since I'm looking at 2/5, not 1/5, I'd have to take this much of it. That's 2/5 of the set, right? With a sharing strategy. So I'd have 4 rods, 4 tenths. What would 3/20ths look like? How can I break this into 20ths?
5 groups of 5.
Cut it in half. And then worry about each column, right? So each 20th is half of a column or half of a row. So each 20th is 5 out of 100. So if I have 3/20ths, how many hundredths do I have? 15. Nice. Okay? So again, if I was using a fair sharing strategy, I would break it into 20 equal groups. I'd end up with 5 little cubes in each group, and then I'd take 3 of those groups to show 3/20ths. But definitely shading is much prettier for this one. Okay? And we want kids to begin to internalize things like fifths and 20ths and knowing that how they can quickly convert those into decimals, right? By knowing their relationship to 100. But now we're going to get a little more challenging and complex because you're my gifted class. What would I do for 1/3?
Figure out how many groups.
33.
How many groups? Let's use fair sharing. If I share this in 3 equal groups, how much goes in each group?
33.
33. So 3 rods and 3 little cubes.
And a third.
Yeah, except I can't call it a third because I'm doing decimals. It's not really a third. I have another little.
3/10.
I have 1/100th left to share. I can imagine that it looks like this too, can't I? And I would share 33 from that, which would be 3 little thousandths and 3 little 10,000ths. And I'd end up with 1 left over, which I could break into 33 and 33 and 33. Are you noticing a pattern?
Yeah.
Okay, so 1/3 is 0.33333. You got me? Or we sometimes write that as 0.3 repeating.
Is it acceptable to just know that 1 0 3
No, you should either put it over the 1/3 or put it with the ... But you only put it over the smallest unit that repeats. Now we're going to do something cool. If 1/3 is 0.3333333 repeating, right? What's 2/3? 0.6666. Whoops.
Sign of the devil.
Okay? 2/3. cool things in
I don't know what
mathematics.
that. I don't know if I agree.
You just used a pattern. 0.3 repeating. Well, this is something we talked to about grade 9s and 10s. It's one of those cool, weird anomalies of mathematics that's like one of those cool things.
So
Like,
ignore it until grade
So
9.
basically, we don't know what she was saying.
not really. These are conversations that came up. Okay? If I multiply 0.3 repeating by 2, I get 0.6 repeating. If I multiply 0.3 repeating by 3, I get 0.9 repeating. But it is equivalent to 3/3, which is 1. 0.9 repeating is equal to 1. If you really want to prove it, it absolutely is. The proof is right there. If you really want to prove it, you have to use limits in calculus. The limit 10 approaches is equal to 0.99999 approaches 1, and therefore is equal to n equivalent to 1. Go and look this, Google this, because I swear it's one of those really cool mathematicians like to prove it kinds of things. It's all over the internet. No, it's actually one. Because this is on forever. Okay, next day we're going to do 6th and 8th, so if you want to, or 6th and 7th, so if you want to play with those between now and next day, you can. And we're going to talk about percents and ratios and all kinds of fun things that are proportional reasoning on the other sheet, and other new things too.